Brownian scaling and self-similarity. Let WT be a Brownian motion. That's a phrase we're going to be hearing quite a lot of from now on, because Brownian motion is the simplest Ito diffusion. It's usually the one we start with in any given modelling situation. So we start with a Brownian motion and then do something to it or make some remarks about it. So okay, we've got a Brownian motion. That means that at any fixed time t, Wt is distributed normal 0t. Wt is the increment of the process between time 0 and time t. At time 0 the value is always 0. That's part of the definition of Brownian motion. It always starts at 0. So the increment between time 0 and time t is just the value Wt, and therefore it has a normal distribution with mean 0 and variance equal to the elapsed time, which is t. Also, if we have W alpha t, so for some fixed multiple alpha is just some positive number. That's to say, we sort of imagine running time faster, then we've got this being true, and therefore this is true as well. If instead of changing the rate at which time flows, we keep just time t, but we multiply the whole thing by a factor square root of alpha, so we just scale the whole thing up. Then scaling up by a factor square root of alpha scales the variance by the square of that, so by alpha. So these two distributions are the same. That's to say, if you run time faster by a factor of alpha, then you're getting the same distribution for where you end up as if you had just run time at the normal rate but scaled everything up by the square root of alpha. In fact, even more than that is true. If you take W alpha t at all times t, so the whole function we're talking about now, as compared to this, the whole function just scaling it, then those two things have the same distribution. And when I say the same distribution for two random functions, I mean really all of the distributions involved with those random functions. If you think of the whole function as a sort of random object and imagine it having a distribution, then it's the same distribution for either of these ways. What's the significance of all this? That comes from these pictures. What we've got in these pictures is one realization of Brownian motion. So you're looking at one random function here, just four different pictures of it. In the first one, we've got t going from 0 to 8, and then we've especially picked out the time period initially where t just goes from 0 to 1, and we've zoomed in on that. So if you look closely at what this function is doing between time 0 and time 1, you can see it looks a lot like the next picture, which is a zoom of the whole thing. Now using up a whole graph to show what happens between time 0 and time 1. And if we then look at the first 1/8 of that, so time going from 0 to 1/8, you look closely at what it's doing there and zoom in on that, we get this picture down here. And finally the same thing one more time, the first 1/8 of that graph, zoom in on that and we get another thing like this. What are you supposed to see in these pictures? Well, what you're supposed to see, which is not that easy when you've only got one realization to look at, but all four pictures have in distribution the same thing going on. They're all Brownian motions. So if I were to just pick a random one of these four pictures, you wouldn't be able to tell which one you were looking at, not even if you looked at many, many realizations rather than just one. Because as far as the distributions are concerned, it's the same thing you're looking at. That's the significance of this fact, this Brownian scaling fact. And what goes for Brownian motion actually also goes for any ito-diffusion, because, as we know, all ito-diffusions look locally over short intervals of time like Brownian motions. So ito-diffusions also have this property that if you zoom in on very local parts of them, you end up looking at something that looks like a Brownian motion. And no matter how far you zoom in, no matter how short the time scale you examine it on, it will still have all of the detail that a Brownian motion has. That makes it a bit different from some of the physical or financial things that we might be using ito-diffusions to model. Obviously, in reality, time cannot be zoomed in arbitrarily. If you look at the way the stock market works, for example, you can look at the way prices fluctuate on a stock market over the course of a day, or over the course of an hour, or a minute, or a second. And I should say that for these prices in financial market type applications, this is sort of true for a while, that the further you zoom in, the more you see it just all looks the same. You have the same kinds of fluctuations going on at short time scales as you do at large ones. But ultimately there is an end to it. Right? At some point you get down to the level of individual transactions on the stock market, and then it looks different at finer time scales than that, because nothing's happening between one transaction and the next. And it's the same if you're using Brownian motion or an ito-diffusion as a model for something in physics. There may be this multiple timescale thing going on, but ultimately you get down to a different sort of level of physical reality. So this idea of self-similarity, that is of the same kind of behavior happening at different timescales, is true in the real world, perhaps over some range of timescales. But for ito-diffusions themselves, mathematically, it's true at all timescales. You can zoom in as far as you like and still get the same distributions for what's going on. Well, since we can zoom in Brownian motion as far as we like, and it'll still look like a Brownian motion at any timescale, that leads to what is called comic relief in the textbook that I took it from, the book by Richard Durrett, Stochastic Calculus. It says that if you run Brownian motion for any positive amount of time, doesn't matter how short the time, but any positive amount of time, it will write your name. Let's just be a bit more precise about what that means. So first we'll have a function g defined on, say, the unit interval, be a continuous function, any continuous function you like. That's supposed to be your name. Right? You think of the graph of that function as being your signature. And let also epsilon be some positive number. That's how closely we're going to expect Brownian motion to match that function in order to have considered it to have written our name. And Tn be any sequence of times that converges to 0, then what we're going to look at is Brownian motion between time 0 and time Tn as an approximation of your name, the function g. So we need to do this. So theta here is the variable, so we're taking that goes between 0 and 1, and we're taking a look at the Brownian motion between time 0 and time 1, except it's not really between 0 and 1, it's between 0 and Tn. We've scaled it appropriately like this, and we've also divided it by the square root of Tn to keep it still the right size, to keep it the same scale as an ordinary Brownian motion. And then we're looking at how close that gets to our target function g. The maximum error is what we want, so the sup or maximum over all thetas between 0 and 1. So that's the maximum difference between our Brownian motion and our target function. And what we want is for that to be less than epsilon. So the Brownian sample path will be within epsilon of the function g over its whole period from 0 to Tn. So will this be true? Well, of course, this is an event, so we should really talk about the probability of it. And the answer is that the probability of that event is 1. For, I didn't say what n was here, so now I have to put in here something like for some n. Actually, I'm going to say more than that, for infinitely many n. So there are infinitely many different timescales on which, if you just keep zooming in and zooming in, there will be infinitely many different timescales on which the Brownian path you find yourself looking at matches your name, the g function, very closely to within the epsilon that we chose. So that really just brings out that we really can zoom in as far as we like, and because we're getting a Brownian motion every time, and because we're getting, as in these pictures, we're getting an almost independent Brownian motion every time, each time we zoom in. In these pictures we're zooming in by a factor of 8 every time, so each picture is almost another independent Brownian motion, except that obviously each one matches the first 1/8 of the previous one. But that aside, it's almost an independent Brownian motion each time. So what we're effectively getting here is a large sample of independent Brownian motions, and since it's an infinitely large sample, it will eventually do everything that Brownian motion is capable of doing. In particular, it will match the function that we're trying to match.